Hey everyone, I'm Ben, and today I'm going to be talking about building a real-time video processor with Swift and Metal. Now, briefly about me, I work on a few popular third-party photography apps, the first of which is Spectre, which is used for generating handheld long exposures, and this was chosen by Apple as the 2019 iPhone App of the Year. But before that app, we shipped Halide, which is designed for manual photography and people who like to shoot RAW. And this makes for a really interesting use case today because we have a portrait mode built into the app that actually is combining several different video sources. The color data that's coming off the camera, and then the real-time depth data that's provided by the system. And we're doing some interesting stuff like creating a bokeh blur for the background. So we'll touch on that a few times today. So today we're going to start off by talking about the architecture of a real-time rendering app. We'll talk about the performance implications, and then we'll round it out by talking about some of the nuances when working with image data. So let's get started by talking about the architecture. So I'm not going to dive into the particulars of hooking into AV Foundation and all the delegate methods, but at a high level, you start out by requesting frames from the system in real time. You just hook into a method and it'll just deliver you video frames at 30 or even 60 times per second. And then you update your internal state every time a frame arrives. So for whatever particular effect or animation, you update it with each frame. And then you issue commands to the GPU to actually do interesting things and eventually render it on screen. Okay? Most of your work is going to start out in Swift, and that's for setting up state and kicking off commands to the GPU. And then all of the interesting work around the pixels on screen is going to be handled by shaders, which execute in parallel on the GPU. And it's important to note, if you've ever dove into game programming, this loop should be very familiar to the game run loop. But instead of having a timer that fires every 60 times per second, we're driving this loop by frames that are arriving from the system. So if you're just diving into GPU programming, that's a lot of the focus of the talk today. And there's two important bits of the pipeline that you're going to want to know about. The first is the compute pipeline, which is pretty general purpose, and you can do everything from editing images to computing Bitcoin. The second pipeline, which is the more traditional pipeline and the entire reason that GPUs exist, is for the 3D pipeline. And you'd use something like that for rendering game scenes. And that's a multi-stage pipeline, and it's a bit more complicated to dive into. So we're just going to start out by talking about the compute pipeline because it's very straightforward. All right? So this is an example of a shader that will run on the GPU, and it's a hello world, where we just get two bitmaps handed to us that we set up previously. These bitmaps are known in GPU talk as textures. And we read from the bitmap, and we just write the value of the bitmap out to the output of this function. So all we're doing is taking in one image, reading a pixel at a location on screen, and outputting at that same pixel on the output texture. And this code is going to run massively in parallel with hundreds of these threads all executing at once. Now, on the Swift side of things, the way that we kick off that shader is through a few bits of code, and I've thrown out a lot of the boilerplate here just to get to the interesting bits. All that you do in Metal is that you say, I want to call this hello world function there in the first line. And you create a pipeline state, meaning I've set up the state so that this function will execute. And you configure your pipeline at launch like this, and you keep a reference lying around so that you can call it later. Then later, as the frame comes in, you kick off in Metal what's known as a command encoder. So that lets you define all the details of how you will execute that function that we defined earlier. So here we assign the input image and the output image to the two parameters inside of that shader. And you can see in the code itself, the texture 0 and texture 1 are special annotations that are later used to glue in those different parameters that we're setting up over on the Swift side of things. And finally, I call dispatch thread groups, which actually kicks off the work, and we say end encoding to say we're done, and then this code will execute asynchronously. So you're always constantly queuing up work that'll be executed with a slight latency. So the slightly more complicated setup is the 3D pipeline. And this is designed for, as I said, rendering 3D scenes. Now, it's still important to understand this pipeline because whenever you want to render something on screen eventually, it's much more performant to render things through the 3D pipeline than to use the compute pipeline because the system can make certain assumptions and performance optimizations. In this example, I'm going to render the world's simplest 3D scene. I'm going to just take 4 vertices that represent the 4 corners of our screen, and I'm going to render a square, and on that square, I'm going to render a video frame. Now, to get there, there are 2 stages in the 3D pipeline. The first one is known as the vertex stage, and if you're rendering a complicated 3D object, what you do at this stage is transfer all the vertices from world space into a camera space and then apply a camera projection, a bunch of math that's not really relevant to anyone in the context of this talk. What's much more interesting is the second stage. Now that all the vertices are transformed, a second set of shaders is executed to render the appearance of the surface. Now here you might come up with a shading model to represent a flat or a shiny surface, but in our case it's even simpler because we're just going to be reading those bitmaps and just putting them out on the surface as textures. What's really interesting is that the GPU is designed to perform 3D rendering and has a bunch of hardware to make certain operations extremely cheap. So for example, let's say that we want to render a point that lies between a black pixel and a white pixel. You'd want to have this color interpolated evenly between the black to white. Actually, in the hardware, it can interpolate for you for very low cost, the value in between. So the question then is, when would you want to use the compute pipeline and when would you want to use the 3D pipeline? Well, compute shaders feel like a better abstraction, right? There's no point in having a pointless no-op vertex stage when you aren't really going to be messing around with vertices, right? So it's easier to reason about. But for complex rendering, like if you were to render something like the group FaceTime video, the GPU can make certain optimizations. So it can tell that one quad, it occludes the other quad, and it can discard the pixels underneath and never render them. Meanwhile, if you try to implement overlapping squares like that using a compute shader, then you're going to have to write your own code to discard the geometry behind it, and you've basically gone and reinvented the pipeline that the GPU can give you for free, and your version's probably not going to be as good as what's built into the hardware, right? Now, in all of this, I said this talk would be about Swift, and let me just touch on a few interesting things that you get out of using Swift as opposed to C++. Well, for one, Swift has pretty straightforward bridging of C structs. Metal shaders are just a subset of C++, so you can just do includes and reuse a bunch of behaviors, pretty straightforward. What's really nice with Swift 5 function builders is that we're starting to see exploration into building domain-specific languages. So I've been playing around with writing a declarative interface for defining how the fragment shaders are glued together with Swift code. It's much cleaner and easier to reason about. So as I touched on earlier, this code is executing asynchronously. So you're constantly getting frames in, you're setting up the work and kicking it off, and you always want to have this sort of like rolling forward and never blocking, which brings us to our second topic, performance. Now, as an example of some of the problems you'll run into, when we are dealing with that depth data that the system hands to us, it is unclamped. So it is not within the 0 to 1 range of values. It's actually representing meters from the camera, so they could be 20 meters away. But if we just take this data that's being handed to us by the system and use that as an alpha mask, or we want to present it to users, you'll see the image on the right, where it's mostly white. So now we're looking at having to go through hundreds of thousands of pixels to find the minimum and maximum values. And we're dealing with as low as 17 milliseconds to do this if we're working at 60 frames per second. Fortunately, we're working at 30 frames a second, which gives us a little more headroom, but still, you don't have a lot of time to work through this. And are we going to start dropping frames? You need to be able to reason through where your performance bottlenecks are, not just for the cases where you do need to optimize them, but also so you don't sweat the small stuff. The biggest secret of high performance is understanding that your bottleneck is not likely in your CPU, but in moving data around. Memory is likely your biggest bottleneck, because even though CPUs have increased dramatically thanks to Moore's law, for the most part, memory access has stayed flat. So the way that the hardware manufacturers got around this is by building memory hierarchies. I'm stealing an example from Scott Myers, who's a noted C++ guru, and he has excellent talks about this that I'll link to later in the talk. But here's a visual analogy of how memory hierarchies work. Now, let's say that you need to access data, and this data is located on the CPU die in what's known as L1 memory. And it takes that amount of time. But if you have so much data that it fills up L1 memory, it will push the data to further away L2 cache, which is slightly slower, but still kind of close to the CPU. And it takes about this amount of time. And if L2 fills up, there's even larger amount of memory that's even further away that takes this amount of time. And some systems might have an L4 cache, but let's say that now your last option is to go reach out to main memory. And it is going to take an eternity. The relative speed on most iPhones is such that L1 cache, which only has 64 kilobytes of memory, that's kilobytes with a K, that only takes 4 cycles to access. L2 cache, which has 1 megabyte, takes 10 cycles. L3 can take 40 cycles, and main memory takes 120 cycles to access data. So that's a 30x difference in performance. Okay, and this goes into a concept that's talked a lot about with Scott Myers and Mike Acton, who's the former engine director at Insomniac Games, and now a director over working on Unity, the game engine. And they talk about this concept, which is data-oriented design, which is to arrange your data in cache-efficient structures and to be able to reason about how data is moving through your system above all else. Fortunately, Instruments has tools based on dtrace, so there are counters available to measure how often you're doing cache misses, although the situation isn't all that good when dealing with the iPhone. But still, you want to be architecting your system from the get-go, thinking about how data is moving through the different pipes, because it's not some kind of problem that you can solve at the last minute. If you've had a fundamentally bad architecture, you're going to have to just rip everything apart and start over. So this has profound implications in how you architect your app. So let's say that you're building something like a Stardew Valley and you're trying to model your crops, which are just grids of, say, wheat. And within each loop, you want to have the wheat slightly grow. So after so many frames, it will be larger or it needs to be watered, whatever. Now, if you're using an object-oriented design, you'd model these wheat patches as classes, and you might even have classes that represent positions. And of course, because we're using an OO model, we wouldn't want to just call height +1. No. We want to send it a message. We want to send it the grow message, which will update its hidden internal state. So the problem with OO languages is that it often leads to pointer chasing with a bunch of objects that are located in a bunch of different random positions in memory, so it's impossible for your CPU to prefetch the data and operate running in a straight line. A lot of OO languages like Objective-C use dynamic dispatch, which means that the CPU will also be missing its instruction cache, which has similar issues. And finally, it encourages you to think of the problem in terms of discrete instances, when very often you're going to be wanting to work with batches of similar data in similar workloads. So what's nice about Swift is that it gives you explicit control over the data layout, so you don't have to deal with a bunch of padding that eats into your L1 cache. You are by default dealing with static dispatch, so everything is able to stay within its instruction cache. And it encourages you to think about value types instead of reference types or objects. So it encourages you to think about data in a way that can be optimized. So what does this look like in application? This is a gross oversimplification, but you could just as easily represent those wheat patch tiles as just arrays of uint8. But that does seem a little messy, because what about all these nice abstractions? We're dealing with wheat patches. We're not dealing with uint8s. Well, in Halide, we still are able to have a thin wrapper around these underlying values. So one technique you might see in C++, they call them strong type defs sometimes, where you just take a value and you wrap it in a struct with only containing that one value, and then you can attach behavior to these structs. You know, there are trade-offs, so you have to go in and out of this struct to do anything interesting. But if you demand type safety, this is a lightweight mechanism to get that. Now, what about polymorphism and sharing complex behavior between your different entities? Okay, so for example, in Super Mario Brothers, you have these Koopa Troopas, and then you have the flying Koopa Troopas with wings, which feels like those should be a subclass of the Koopa Troopa, right? Well, the problem you'll often run into in modeling is you end up with these hierarchies which seem to make a lot of sense up front. But then as soon as you have cross-cutting concerns, for example, Goombas, they can also fly. What do you do there? Right? Do you subclass the Goomba also? And how do you duplicate the flying behavior? Well, one problem is that you end up with multiple inheritance, which is the road to insanity. Or you've heard the old phrase, favor composition over inheritance, where you'll have, say, a flying component which will sit inside of each of those separate instances of these enemies. So, in fact, if you take a step back, you could just define these different enemies as just these sort of abstract entities, and each entity has behavior. You could have power-ups be another type of entity. You could also have flying mushrooms. You could mix and match this however you want, and also, from a product perspective, makes it very easy to prototype behavior without having to go into your object hierarchy with a chainsaw and dramatically refactor everything to support this random flying behavior, right? And so this is the idea behind entity component systems, where you just define these abstract entities. They have data attached to them, like life force, or they could have velocity, they could have mass. And the interesting logic exists in these systems which operate on the entities and their components. And you'll see this pattern is becoming more and more popular. So for example, the Reality Kit framework, which Apple launched last year, WWDC, is actually based on a rich entity component system. So in all of this, even if you're going to continue to use all the existing patterns that you're using in user-facing apps, really think about data-oriented design and these solutions as a way of thinking more than a proscription of how you should design your apps. So what is data-oriented design in the end? Well, here's an example. Let's say that we want to blur this image on the left. And a Gaussian blur, it scales at big O of n times r squared. So what that means is n is the number of pixels in the image, and r is the radius of the blur. So as the blur gets larger and blurrier, it takes exponentially more time to actually compute. Well, there are different solutions. There's different algorithms that can approximate the Gaussian blur, but here's a very simple trick which requires little effort. What you do is you shrink down the original image to half its size, which is about a quarter of the number of pixels, and then you blur it, and then you upscale it to the original size. I think it would be a challenge looking at these two to tell what's going on here. So with that, let's segue to the last detail, which is working with this image data. Okay, so you've got your engine working. You're processing images. You're ready to output this image of a flower on screen, but then when you actually go to render it, it's all red. So you'll find that actually the data that's being handed to you by the system is not encoded as RGB values. It uses this weird encoding called YUV. The first color channel that is handed to you is just the brightness value. Then the other two channels represent the color. So these color values are actually coordinates on this UV color space, the amount of blueness and the amount of redness. That's why sometimes YUV is called YCBCR, color blue, color red. From a distance, it looks like the kids in this photo have different colored shirts. But if you zoom in, you'll see that actually the shirts have this crisscross pattern of colors, and our minds are filling in the color in between. And this is because the human visual system is much better at spotting differences in luminance than in color. So graphics engineers have exploited this to save the amount of bytes that have to be passed through the system. What we do is we split this image into its luminance data and its color data, and then we shrink down the color data. And then at render time, we can interpolate between it, and our eyes can't really spot a difference. Now, this all sounds really complicated, but in practice, you just need to copy and paste a simple shader. You've got this YUV data, and it's converted to RGB data. It's simple, but for whatever reason, it's not part of the iOS standard library. The code itself, if you need the example, is listed in the ARKit documentation. And if you just copy and paste this metal shader, it'll all get the work done for you, no sweat. It's important to understand that the textures handed to you by the system will tell you what the different values are, if it's a 4-channel image or a 3-channel image or a 1-channel image, but it doesn't give you any type checking as to what the content of that pixel buffer is. Is it encoded in RGB or is it encoded in YCBCR? Well, you could check the property on the metal texture to get that value, or you could write a lightweight wrapper in Swift that will give you some type safety. So here I've begun wrapping my textures inside this exhaustive enum to explicitly say, this shader that I've written, it's expecting a frame that's in YCBCR. You just can't hand it an RGB texture. I have no need to write that shader, but I want to make sure I don't accidentally do that later and hand it the wrong type of color value and then waste 2 hours on a stupid type bug. So here I've just written lightweight wrappers just around metal textures to give me that type safety. So we've got it so that we're rendering an RGB image, but then we display it on screen and the image is a little too dark. Well, now we're going to get into a topic that plagues beginning graphics engineers. It has to do with something called gamma. So let's say that we need to render a gradient on screen, and we want a very smooth transition of this gradient from black to pure white. In fact, if we were to draw a gradient that just loops through pixel values from 0 to 255, it would actually look like the gradient on top. The gradient on bottom, which is perceptually uniform, that 128 is located all the way over on the right. And this is problematic because that doesn't give us enough shades of shadows to work with to give a very smooth gradation in the gradient. And this has to do with how our eyes are much more sensitive to shifts in shadow than they are into shifts in the highlight. Here, deliberately used only 128 bytes to represent the lower end of the spectrum, which creates this very ugly banding. And if your monitors aren't properly calibrated, I deliberately brought up the brightness to help highlight how bad it bands in the lower end. So the solution that engineers came upon code the pixel values with a curve. So what ends up happening is you take a photo, and even though the scene is all linear data, it's all linear light, before we save it to a JPEG, we apply a curve to make everything sort of brighter so that all the shadows have more bytes to work with. And then when we go to display this data later on screen, your monitor will apply the opposite of that curve so everything looks correct. So this is known as gamma encoding and gamma decoding. And this is a source of a huge number of bugs, especially for beginning graphics engineers. Gamma bugs are so common that Photoshop used to have this ugly artifacting when you'd use a brush on an image and it would blend in the background with its alpha. So you'd see this black matte like in the lower left. In fact, Adobe later had to add a backward compatibility checkbox to continue to have that gamma bug for the artists who are used to this behavior. So in all of this, the most important thing to understand is that you don't fix these problems by tweaking values. 3D artists, when they're first getting started writing rendering engines, they'll try to adjust the lighting because they think, oh, it's really dark, what's going on? When it has to do with their fundamental lighting algorithm. You want to fix the gamma bug itself rather than try to patch over it by poking and prodding values. And it is not difficult. There is boilerplate code that tells you how to gamma encode and how to gamma decode values. But again, unfortunately, it isn't part of the standard library, but it's literally the last page of the metal shading language specification. Okay, now we're ready to display it on screen. And if you don't have a sharp eye, you're going to miss this last bug. So here I've deliberately cranked up the values a little bit to highlight what's going on, but you'll notice that the color values that you're seeing in the scene are slightly different than what's being displayed on your screen. Okay, what's going on there? And this is a relatively recent problem. The colors in the natural world that your eyes can perceive are represented by this horseshoe shape you see on screen right now. This is the entire visual spectrum, and that little triangle in the middle is the sRGB color space, which is what's available in the vast majority of monitors in the world. When you're displaying something on the web, more likely than not, it is using the sRGB color space. Okay? And this wasn't a problem for a huge amount of time until Apple went out there and created new devices that supported even wider colors. So the problem is, what happens if your color values are written expecting the triangle to be in that smaller triangle, when in fact you're writing to a color space that's in the larger triangle? Well, all of your colors are going to shift around and they're going to be located in the wrong spot and everything's going to look incorrect. Fortunately, this is also not a difficult problem to solve. Most of the difficulty is keeping track of the color spaces you're working in. So understanding the color space of your source image and understanding the destination color space that you're displaying on screen or you're writing to disk. So all I have to do is attach another property to my frame wrapper that I'm passing around, and the compiler can help me out with catching these little bugs. And there you go. You've got a frame rendered on screen. So what did we cover today? Well, we went over the core render loop and where your performance bottlenecks are going to be in that. We talked about the role of shaders and how they work on the GPU. We focused on designing data structures that can lean into the GPU and take full advantage of its performance and recognize where the memory bottlenecks are. And finally, we talked about YUV, gamma, and dealing with color spaces, and touched on a bunch of the theory in rendering images on screen. So thanks for attending my talk, and now I am available for questions in the forum.